Hello everybody, this is Dr. Christopher White and welcome to this video looking at the lab exercise Interpreting Geologic Maps. So as we previously discussed, geologic maps are pictorial representations of the geology for a given area. So we know on these maps there is a whole lot of geologic data, so obviously you have the colours and the labels for each of the different layers of rock and formations. You have things like faults, you have the trends of folds, you have structural data, you have important occurrences, so things like veins or areas where certain minerals have been located. You can even have other information, including things like metamorphic grades. And then all of that information is, of course, placed onto a pre-existing topographic map. So you also have the additional information for things like contour lines, you have the locations of buildings, roads, rivers. So there's a lot going on your geologic map. Now, as we've also touched on, the reason for using the contour map to produce the geologic map is, number one, it's nice to have a map to work off. But the presence of the contour lines in particular are extremely helpful to geologists because they allow us to produce a very accurate topographic profile for any cross-section that we are producing. There is also an additional bonus that, of course, because we have all this added information, so things like the location of important buildings, it does allow geologists to orientate themselves correctly when they are using the map for field work. So when it comes to producing modern geologic maps, there is a two-step process that's employed. So the first step will use existing data to roughly define the important information. So, where are the boundaries in the rocks located, any major faults, any major faults. And then obviously once you've got all that information combined into your first stage geologic map, you can then go to the area and actually make sure that the boundaries are where you think they are, and if they're not, you can make adjustments as required. So what pre-existing information will geologists look for to produce their stage 1 geologic map? So the first thing that a geologist is going to do is they are going to try and find any existing geologic maps for the area of interest. Now, there are some areas of the Earth's surface that have been very, very intensely mapped from a geologic standpoint. However, these areas tend to be associated with concentrations of valuable materials. So we're talking about sedimentary basins that produce oil and gas. We're talking about areas that maybe have minerals of economic interest, so maybe coal seams or copper ore, that kind of thing. However, these areas are the exception rather than the norm. So for the majority of locations, you are going to be dealing with a situation where you maybe have one, possibly two geologic maps, and they would have been produced sometime within the last 100 to 150 years. So often there is a certain amount of data on those maps that's either going to be incorrect or out of date. The other thing that needs to be borne in mind is that for the geologic information that's available on these maps, it's typically only limited to areas that were easily accessible. So if there's an area in your field area of interest that would not have been easily accessible 100 or 150 years ago, there is the possibility that that area has not been mapped at all, or if it was mapped, it may have been done visually from a distance away. So there may be quite a few assumptions made for that particular area. So using these older maps is something that must be done with great care. Now, the reason for this is obviously because when they were producing these older maps, it was geologists going into the field, going to every single outcrop they could, and then they would also walk some transects, so they would walk some lines, some going north-south, some going east-west, and they would obviously collect all the structural information they could for an area and all the information about the lithologies which were present as well, and use that to produce the geologic map. However, in a lot of cases, they were not using accurate topographic maps. So maybe the map they had would have had something like a river running through it, and that would have been the point of reference from which they would have located the position of the boundaries that they found. However, over time, maybe the position of the river has moved. You can also imagine a position where the geologist might have taken their measurements from a structure which is no longer around. So if we think back to our aforementioned river, maybe there was a mill on that river which they took their measurements from and the mill is no longer there. Or maybe they took their measurements in a hilly area and they used the intersection between two farm walls which are no longer around. And so you can begin to see quite quickly how, although these old maps are often extremely accurate and very good, there will be inconsistencies with them that mean that they are not suitable for modern day uses. Another issue that sometimes occurs is with the projection system that's being used to produce these maps. So the first thing is a lot of the time these older maps will have been produced maybe using longitude and latitude, and of course they will have had to have taken measurements in order to calculate where they are and to get the latitude and longitude coordinates for certain points on the map. Obviously, there are going to be issues with calculations, mistakes can be made, and then there's also the problem that modern day maps tend to prefer to use UTM as the map projection, and so this is obviously also going to be an issue because you're trying to convert information from longitude and latitude to UTM. And so once again, there is the possibility that mistakes can occur, and as such, you have to be careful when using these older maps. So the next source of information that geologists will use are satellite images. So modern day satellite images have extremely good resolution, and obviously it allows you to zoom in and out of the area so you can get in as close to the ground as you possibly can, or you can obviously zoom out to get a broader idea of what's going on. Now, satellite images are extremely helpful because the first thing you can do is you can look at them and you might be able to spot the trend of geologic features for the area of interest. So you might see a distinctive kind of zigzag pattern to the topography, which would suggest there could be anticlines and synclines present. And from there, you may even be able to start getting a rough orientation for those structures. You could also look for things like fault scarps, which would, suggest that maybe there is a fault below the surface, and so you can also begin to put that information into your preliminary map. Now, another thing you can do with satellite images is you can hunt around and you can actually find areas of exposed rock. In the first case, this is extremely helpful to geologists because it tells you where you need to go when you're actually in the area to collect the rock samples. The other thing you can do is you can actually look at these satellite images and you can begin to look at the color of each of these outcrops. And if you happen to have some outcrops that have a rather distinctive color to them, so let's say, for instance, you have a group of outcrops that's showing a distinctive white color and maybe another group of outcrops that's showing a distinctive dark gray color, well, you can use that information to begin to say, right, I think these outcrops contain lithology 1 and these outcrops contain lithology 2. And so you can start to begin to get an idea of where the beds of rock might be trending. Another thing that you can do with satellite images is you can analyze them using GIS, or Geographical Information Systems. And so what this means is it allows you to take the image and split it into layers, split it into parts. And if you use the correct techniques, you can actually begin to subtract certain things from the image, and that will then allow other things to become visible. So the classic example of this is vegetation. So if you imagine a situation where you have a satellite image of an area and you want to look at the surface below, however, it's quite heavily vegetated. Maybe there's lots of trees, and so obviously the surface is obscured. Well, what you can do is you can use GIS, and that you can actually subtract the vegetation from your image, and then that will allow you to view the ground surface below. And then once again, you can look for things like certain patterns that could suggest certain geologic structures. So there is a lot of information that you can get from these satellite images that's going to make your life very easy. And of course, the final thing for satellite images is that they give you access to areas that you may otherwise not have access to. So, of course, if you think of an environment maybe like the high northern islands of Canada, so right up there in the Arctic, most of the time, very difficult to get to. Geologists can't really go there. However, you can use satellite images. You can get a really good idea of the geology of the area before you even have to head out to that location to collect any data. So it means that you can get into these areas, you're really well prepared, and so you can do your work quickly, and you can also therefore do your work in a more cost-effective fashion, which is always really quite helpful. So the third source of data that you can use is geophysical data. And in terms of geophysical data, arguably the most common types used will be gravity and magnetic surveys. And these are favored because they can be taken using an aeroplane mounted piece of equipment. And so these gravity and magnetic surveys, they're not high enough resolution in most cases to allow you to pick out individual layers of rock. However, what they can do is they can allow you to discern certain trends in the strata. And so you can begin to see the orientation of maybe one band of rock, and you begin to see the other, and you can see things like large anticlines and large synclines, and in some cases you can even spot the position of faults. Now, another thing that you can do with geophysical data that you can't do easily with other types is it allows you to analyze areas that have had quite a lot of igneous activity in them, especially intrusive igneous activity. So if you imagine a situation where you have an area that once upon a time was part of a convergent plate boundary maybe, and of course that means the area is going to be absolutely stuffed with intrusions of things like granite and tonalite, and it's actually going to be quite difficult to discern approximately where the boundary of each of these intrusions is located. However, if you use the correct geophysical technique, let's say gravity, there's a pretty reasonable chance that you will be able to approximately mark out the boundary for each of the larger granite intrusions. And obviously that's then helpful when you are producing your geologic map, because you have a starting idea about where the margins of each intrusion will be located, so you can separate them out more easily. So once the initial analysis of the area has been completed, you will then send geologists out into the field to begin actually analysing the area in greater detail. And so geologists are going to access the area by foot, maybe they'll go in by vehicle, or in some extreme cases, if the terrain is quite difficult, maybe even by helicopter. And so they'll collect information that will help to confirm or refine the initial map that has been produced. So it'll help to mark out, exactly where the boundaries are located, for instance. It'll help to mark out the positions of things like anticlines and synclines. It'll help to also, definitively mark out the position of things like faults. Now, another thing that's going to be taking place during this time is, of course, the geologists are going to be going to all of the outcrops they possibly can, and they're going to be classifying those outcrops and taking rock samples to bring back for lab analysis. And then, of course, they'll also be analysing any fossils present, not only to work out the environment of deposition for the rock in question, but also to allow them to put each of the units into the geologic timescale. Of course, this is going to be important later on when it comes to the stratigraphic column, which is located next to the map, because having this information allows you to put the rock units in the right order, and obviously having the rock samples also allows you to give the descriptions for each of the units shown in the map as well. Of course, the final piece of information that's going to be collected is structural information. So that's going to be things like dip direction, and strike for layers of rocks. It's going to be the plunges of folds. It's also going to be the dip and strike for things like faults. And so all of this information is then going to be used to refine the initial geologic map produced, and then thereby produce the final definitive geologic map for that area. So as we've discussed in the past, once you've produced your geologic map, you're going to assign each of the lithologies and formations their own distinct color or pattern. And of course, you're then going to give them a letter name associated with them. And of course, we've already touched on how the first letter of this code will typically relate to the age of the rock that you are looking at. So once you've done that, you're going to take this information, so the colors that have been assigned to each layer, combined with the dating for each layer that you've done, and the rock descriptions, and of course you're going to combine that into the stratigraphic column, which is going to be associated with your map. And obviously next to the stratigraphic column, you are going to have descriptions for the lithologies associated with each layer or formation. You're also going to have additional information on your map. So you obviously are going to have a scale bar located beneath your map so that you can get an approximate idea of the sizes of each of the structures. And you will typically also have anywhere between 1 and 3 cross sections located on your map as well. Typically, you will have 2 or 3 cross sections, and this is because the cross sections are orientated to allow you to view the geology from different orientations. So maybe you'll have one cross section located north-south and one cross section orientated east-west. So by using cross sections with different orientations, it allows geologists to view the strata, so the subsurface geology for an area, from different orientations. And of course, this is going to be helpful when you're trying to envisage the geologic history of an area and how it's developed over time. So now let's start thinking about some of the map symbols that you might see when looking at a geologic map. Now, some of the symbols that you will come across will already be familiar to you, things like contour lines, the outlines of buildings, rivers, roads, etc. You know, you've seen them on topographic maps already, so you know what they look like. Now, in the case of the geologic portion of the map, obviously, it's going to have its own distinct set of symbols. Now, if you look on any map, you are going to find a key that's going to tell you what each symbol means. There will be variations depending on where the map was produced. However, the symbols themselves will typically be the same. However, there may be variations in things like color or maybe line thickness. So the first and by far and away the most common symbol you're going to come across on a geologic map are boundaries, sometimes also referred to as contacts. And these represent where you have two different lithologies against each other. Now, typically when you look at boundaries on geologic maps, you will see they'll come in two broad types. There will be boundaries that have a solid black line, and there will be boundaries that have a dashed black line. And the reason for this is relatively straightforward. In a lot of cases, you will not actually be able to see the boundaries between the layers of rock. There will be cover over the top, which will stop you directly viewing it. However, you do have access to techniques that will allow you to infer the position of that boundary. And so the solid black line denotes areas where we are totally certain that the boundary is located because we can visually see it. In contrast, the dashed line here denotes areas where we have inferred the presence of the boundary using geologic mapping techniques. We are typically quite confident about where the boundary is, but we use the dashed line because we are just, saying we are 99.9% sure we know exactly where it is, but there's always that possibility we could be just maybe a little bit wrong. Now, another type of symbol which you will definitely have already seen is the dip and strike symbol. And of course, they have this rather distinctive T-like shape. And if you remember, there's one side that's longer and one side that's shorter. So the longer side represents the strike, the smaller side represents the dip direction, and the value represents the dip angle for your layer of rock or for your structure, let's say a fault. We also saw in an earlier lab this symbol here, which is a circle with a cross in it. This, of course, denotes horizontal bedding, so it has a dip of 0 degrees. The final symbol is the symbol for vertical bedding, so bedding that has a dip of 90 degrees. And as you can see, it has this distinctive cross shape. It looks quite similar to a dip and strike symbol, in fact. So each of these symbols that you can see in this figure here are going to be extremely common on geologic maps. You are going to see them a lot, and they are going to be extraordinarily helpful when it comes time to produce geologic cross sections, because obviously they're giving you the information about the orientation of the layers of rock that you will be drawing as part of your cross section. Now, another feature that you are going to commonly find on geologic maps are faults. Now, faults will typically be marked by a black line, and just like the lithologic boundaries, the line can typically be solid if we are absolutely certain where the fault is located, or it can be a dashed line if we are a little bit uncertain and we are inferring the position of the fault. Now, faults obviously come in three types: normal faults, thrust and reverse faults, and strike-slip faults. And they are going to be given their own symbols on geologic maps in order to make distinguishing them, as easy as possible. So in the case of normal faults, you will have a line on the surface. Like I said, it can be a solid black line or a dashed black line. And this line can typically have a few different symbols associated with it. So you can sometimes have a small tick, or you can have a box associated with the line. And the tick and the box are denoting the side of the fault that has been down thrown, the side of the fault that has dropped down relative to the other block. It's also very, very common when you see faults on a geologic map, if they are a normal fault, that the up thrown and down thrown side will also be labeled with the letters U for up thrown and D for down thrown. And so this is giving you an idea of which side of the fault is dropping relative to the other side. Now, even if you don't have U and D on your geologic map, the presence of the tick or the square is going to tell you which side of the fault is dropping down, because they will be located on the down thrown side. You may also be lucky, and in some cases there will even be a dip value associated with the fault plane. And so this means you can draw the angle of your fault in your cross-section with a very high degree of accuracy. However, the presence of a dip value is it's somewhat common, but it's not super common on geologic maps. And the reason for this is we can infer the position of the fault due to something like a fault scarp. However, we can't get a direct measurement on the fault plane itself, so we can't get an exact dip angle. And so in those situations, you will not have a value associated with your fault plane. However, you know which side of your fault is the down thrown side, because it will either be labeled or you'll have a symbol to tell you. And so you know which way your fault plane is going to be angled. And you also know that normal faults tend to be quite steep. So they'll have a dip angle of typically of somewhere between about 70 or 90 degrees. And so you can put in a best case dip for your fault. So in this case, I've used 85 degrees. Now, in the case of reverse and thrust faults, you will have a black line denoting the location of the fault, and it will have accompanying triangles which are located off the fault plane. These chevrons are giving you information about the orientation of the fault plane. Now, in some cases for thrust and reverse faults, the down thrown and up thrown side may be labeled. However, it's not particularly common. So most of the time when you find a reverse or thrust fault on a geologic map, you will see this distinctive sawtooth pattern, and it's these triangles, the teeth, that are going to give you the information about how the fault is moving. So when you look at these triangles, in this case, you will see that the point of the triangles is pointing into the up thrown block, the piece of rock that's being pushed over the top. So if you look at it in cross section, what we have here is we have the down thrown block in yellow and the up thrown block in green, and you can see that the triangles are pointing towards the right, and so that would be this side of the cross section. And so the triangles themselves are pointing down the dip of the thrust or reverse fault. And so using the triangles, you can work out the orientation of the fault plane, and you can also get an idea of the sense of movement, because even if we didn't have D and U on our diagram, we can use the triangles and we can say, right, based on the triangles, this side of the fault is the up thrown side, so this is the side that's being pushed over the top. So the sense of movement on this fault would be the rock is being pushed from the right towards the left. Now, in terms of thrust faults themselves, when you put them on cross sections, once again, it's typical that you will not have a dip value associated with your thrust or reverse fault. So normally what you will do on your cross section is you will put in a generalized fault angle. Typically, reverse and thrust faults are quite shallow in their angle, so you might go for an angle of like 10, 15, or 20 degrees. Now, the third type of fault are strike-slip faults, and they are going to be denoted by two half arrows on the surface that give you an idea of the sense of movement. So in this case, you can see that the yellow block is going upwards and the green block is coming downwards. So this is going to be a right lateral strike slip fault. Now, when we view strike slip faults in cross section, they are considered to be vertical. So they're given a dip of 90 degrees. You will also sometimes see these two symbols associated with strike slip faults in cross section. The circle with the diagonal cross in it denotes the block of rock that is moving away from you, whereas the circle with the smaller black circle within it denotes the block that is moving towards you. And so even if you didn't have this part of the map which shows you the sense of movement, you can use the presence of these symbols to say, right, the right-hand block is coming towards me, the left-hand block is going away from me. This is clearly a right lateral strike slip fault. So this is going to be a good place to stop part 1 of this video. So if you could get up, have a walk around, get yourself a glass of water, and then return in a few minutes to begin watching part 2.